Here is a parent function. It's the parent reciprocal function. If you'll remember, it had a vertical asymptote at x equals 0, a horizontal asymptote of y equals 0. It is an odd function because it is symmetric about the point of origin. If I take that parent reciprocal function and I explore what would happen with this function, I want to notice some things. I still have the same domain for this function that the parent reciprocal function has. I have to throw 0 out, can't divide by 0. But all other real numbers are legal for me to put into this function. One thing that I want you to look at is what happens when I put a negative value into this function machine. This takes everything that I feed it, puts it in the denominator of a fraction where the numerator is 1, and squares it. Every single output of that function is going to be positive. All of them are going to be positive. So everything that's going on here to the left of the parent reciprocal function that would give me negative outputs is forced to be positive outputs for this function. So I want you to think about what operations are happening, whether they're happening in the numerator or the denominator. What's happening to all as a set, all independent variable values that are legal for you to use? Is this function analytically an even function? Even functions analytically are proven to be true using that statement. When I feed it a negative value, the negative disappears and I get the original function back. Well, here's my original function. It's 1 over whatever I feed it squared. If I feed it a negative x and I clean it up algebraically, that's what I get. Well, that was my original function. Analytically, I have proven that this is an even function. I can see graphically it has the attribute of being symmetric about the y-axis, and that just backs up what I determined about this function's symmetry. Let's talk about transformations of functions where this is our parent function. What I'm trying to get you to see here is we're going to be dealing with functions, many more than I've given you as our parent function list, but the idea of reflections and translations and stretching and compressing is still going to be true no matter the makeup of the original function we start with. Some things that we've learned are still going to be true. If we take a variation of this function and we do something inside the function operation, we're going to see a horizontal change. Specifically, we're going to see a horizontal translation 2 units to the right. Everything that we learned about our parent functions is still true here. If we have a change on our function that is happening outside of the operation going on your independent variable, that is going to be a vertical change. Specifically here, we're moving up 1 unit in the plane. I wanted you to see that no matter what function we start with, we can still get a good idea of the changes that are happening on functions that look like that based on our knowledge of what we learned with our parent functions. I want to talk about function composition. There are several mathematical operations. We know a lot of them: addition, subtraction, multiplication, division, trigonometric operations. Take the sine of something, the cosine of something, the tangent of something. Exponential operations. Take an independent variable and make it an exponent to the base of, let's say, e. Logarithmic operations. Well, those are generic functions, f of x, and we'll say g of x. Just two arbitrary generic functions. We can compose these functions and come up with brand new, unique functions. If I take g of x and I pop it into the f function machine, f takes everything I feed it and does some sort of operation on it. I could come up with a function where I take f of x and pop it into the g function machine. Whatever operation g is doing, it's doing on the entire function of f, not just on the independent variable x. So I'm not going to go through this specific example, but if f of x were 1 over x and g of x were the square root of x, you can follow through the two different types of composing functions in either direction. There are two notations. This one is what you will see most often, but you do need to recognize that that just means composed as well. This is the inside function. This is the outside function. This function was put into the g machine. So make sure that you can talk about f of g of x and g of f of x no matter what specific functions you might be given. Finally, let's talk about data tables. A function is most clearly expressed when it shows how specific inputs are assigned to corresponding outputs. It's why we like graphs. Graphs make it very easy for us to see what the result is at any particular independent variable value. So we tend not to like tables that much. But I want you to understand tables of values are just snapshots of several different points in the plane. That's all they are. They're just gathering points. This one probably is most easy to see. Here we have the point 0, 5. We have an x value of 0. There's the independent variable. When we put it in this function, it yields us the dependent value, y equals 5. The next point is 1, 8. The next point is 2, 11. Here, we're looking at point sets. We always list the independent variable first, then the dependent variable. So time is always going to be our independent variable. We had that discussion before. So the points here would look like 1960, 100. There's 1 point on that function. 1980, 15. There's another point. And what I find is that students, many of them, dislike tables of values so much that they will take the time to graph whatever point pairs they were given so that they can look for trends, increasing, decreasing, linear, nonlinear. You are going to have to do this without taking the time of graphing the point pairs. You are getting prepared for a timed test next May. We're not going to do anything that eats up our valuable time where we could be doing calculus. So I want you to practice looking at data given to you in a table and answering the questions that you would normally answer if you were looking at a graph. That takes practice, and trust me, I'm going to give you a lot of practice between now and next May to be able to do that. This finishes up all of our videos for pre-calculus. You need to get yourself ready for homework the next time we meet on these concepts that we just covered, and more importantly after that, you need to get yourself ready for your exam.